Okay, in the last class we were talking about quasi-periodicity, mode locking and things like that, and in general I told you that such phenomena occur where there is a scope of having two or more frequencies in the system. Like for example, suppose there is a pendulum and the pendulum's bob is given an additional sinusoidal perturbation. So, there is one natural undamped frequency of the pendulum. I mean, if the additional forcing were not there, then it would have oscillated with a certain frequency, and in addition to that you have added a frequency component to it. So, there should be a interaction between the two frequencies, as a result of which the phenomena that we are talking about might happen. There are also situations where you would normally not expect any sinusoidal oscillation. For example, those who come from electrical engineering know that there are a class of power electronic circuits known as DC to DC converters, in which you only have DC voltages. There is a DC input, there is a DC output, so you do not expect anything more to happen, except for the fact that these are switching converters. So, there should be switch on, switch off, switch on, switch off. So, there should be a characteristic time period for which the switch ons and switch offs takes place, and so one frequency is easily identifiable. But the other, it has been found that when the parameters are varied across a certain parameter value, suddenly a very slow sinusoidal oscillation develops, and that has been recognized as a very lingering problem of DC to DC converters. In such situations, it will not be easy for you to visualize where did that additional frequency come from, other than looking at the mathematical analysis of it. So, you have a normal operating condition is a limit cycle. You place a Poincare section, look at the fixed point, take a local linear neighborhood, and if you find that a pair of complex conjugate eigenvalues are going out of the unit circle, you know that that is what should happen. That should result in the creation of another frequency component. So, these things are often very perplexing for mainstream engineers, but once you have this viewpoint, this mathematical viewpoint, things become relatively more straightforward to visualize. But in general, when we are trying to understand the phenomenon of dynamics on a torus, it will be easier for us to picture situations where we can clearly identify two possible frequency components. As I told you, one possible thing is simply to visualize a pendulum with the bob would move in a to and fro motion with a certain frequency, the natural undamped frequency, and that would be 1 by twice pi root over g by L, no. So, that would be the frequency of oscillation if there had not been any additional forcing, but supposing it is given additional forcing a sin omega t, that omega, the frequency associated with that omega is an additional frequency component. That immediately tells you that there are two ways to picture the frequencies. One frequency in this case is the additional frequency that has been imposed from outside, but here what is the frequency of this fellow? This is what we have written, that is the frequency, that is the small amplitude frequency, that means the frequency that you can identify under linearization. Okay. So, that is the natural frequency identified under the assumption that the oscillations are not very large. So, in that case it would be a linear system on which you have given a sinusoidal perturbation. But of course, in a linear system you are not allowing it any scope for the two frequencies to interact, right. In a linear system, if there is no nonlinearity, then they cannot interact really. If you add some nonlinearity, in this case if you simply do the modeling of the pendulum and allow the pendulum to oscillate over a large amplitude, it becomes a nonlinear system, right. So, in actuality the frequency will not be this, in actuality the frequency will be something else. So, you can identify two types of frequency ratios. One is called the omega, which is simply f1 by f2, where these two, I mean, if f1 is the frequency imposed from outside and f2 is the natural undamped frequency here, then this omega is the ratio. Therefore, it is not the ratio of the actual frequencies. The actual frequencies of the system is not the ratio of that. This omega is a sort of idealized ratio. It is called the frequency ratio parameter.
And the forcing frequency.
Yes, yes.
But while you are forcing, if you solve the differential equation, you will generally find that it's basically the forcing frequency by which it oscillates. Not
Yeah, that's true. Ultimately, it will oscillate at the forcing frequency. Agreed. But still, we can identify a number like this, because if you do not apply the forcing, it will oscillate at this frequency, and you have given the forcing, and therefore you can identify, at least in theory.
So omega is that should be these two frequencies, those two frequencies.
Yes.
It's not the actual.
No, it is not the actual frequency of oscillation. So, it is just the frequency ratio parameter, somewhat idealized. But the actual thing is called the W parameter or winding number, which is f2 prime by f1, where f2 prime is the actual frequency of oscillation of the bob. So, in this case we are allowing the nonlinearities to play. In this case we are allowing the nonlinearities to come into the picture.
f1 prime by f2 or f2 prime by f1?
Oh, this one would be f2 by f1. Sorry.
So f1 is the natural frequency.
Yes. No, f1 is the externally imposed frequency, f2 is the natural frequency, and the f2 prime is the actual frequency of this oscillation, taking into account the nonlinearity. What?
What is W called?
This is called the winding number. Actually, this is the more important thing, because that is what actually you see in the system, right? That is what you actually see in the system, and this is sort of idealized value. And it is not difficult to see that if the winding number is a rational number, then you have a periodic orbit, and if it is an irrational number, you have a quasi-periodic orbit. So, which means that ultimately our point of concern is the winding number. That is what distinguishes between periodicity and quasi-periodicity, the winding number. Okay. Clear? So, suppose the winding number is 2/3, 2 by 3. In that case, what will you see happening on the torus? Imagine the torus. And imagine that you have placed a Poincare section here. What you will see on this Poincare section? Essentially, you will see something. The section of the torus would be a circle, all right, but you will not see the circle, because it is, in this case, when W is equal to 2 by 3, in this case it is a rational ratio, and therefore you will see a finite number of points. How many? 3 number of points really. So, what will happen is that say the three points are here, here and say here. So, starting from here it will go around it and will hit it somewhere here, will go around it and will hit it somewhere here, and will go around it and finally come back here. That is what the behavior is. So, by the time it makes 3 rounds in the big circle, it makes 2 rounds on the small circle, and that is why the ratio is 2 by 3. Okay. Now, yes.
How will we differentiate the irrational and rational numbers? And in the sense that suppose this f2 prime and f1, how can we say that it's irrational or rational in a real system? Like we cannot always say that it's exactly 2 by 3 or whether it's
I'll come to that. That of course, his question is how can you really say it is rational or irrational, because in immediate neighborhood of every rational number there is an irrational number, in the neighborhood of every irrational number there is a rational number. How can you say that? Yes, that of course you say with finite precision of your calculation, but soon we will see that we can do a lot of coarse grained calculations. Soon we will see. Just wait till the end of this class, I will explain how. Because of the mode locking, because as I explained in the last class, the mode locking happens for a large parameter range. So, the rational ratios will be happening for a large parameter range. That is what allows us to even by a rough calculation, even by a finite precision arithmetic, to calculate, to find out that it is really a rational ratio. Okay, but we will come to that. The point is that let us now develop this circle here and see what is happening. Suppose here is a circle, and suppose there is a point, not exactly this situation, supposing another situation, initial point is here, and before coming to the next one it has gone around once and fallen here. It is possible. Now, will the Poincare section be able to distinguish between these two situations? No. That means started from here, and when I just explained, I said that it goes around and comes here. Supposing it does not do so, rather it goes around, it goes around, and by the time it comes here, it has gone around this once and it has come here, suppose. Then looking at the Poincare section, we will not be able to distinguish it, right? And that is why when you talk about these mappings, there is no point talking about these 2 pi rotations. That is why you always take a modulo 2 pi. That was we always take a modulo 2 pi. Or if you say the whole rotation is 1, then we take a modulo 1. You understand what is modulo 1? That means you subtract all the whole numbers. That means if you have something like if the winding number comes out to be say 1.7, will simply this is equal to 0.7. As far as the Poincare section is concerned, 1.7 is same as the 0.7. Okay. But we have to understand that something has gone on. That means it has gone around the small circle without intersecting here. It has gone around the small circle one more time. We have to keep in mind, but on the Poincare section that might not be visible. Fine. Now let us come to a very simple situation by which we can understand these things. Whenever we were talking about dynamics, we essentially were talking in terms of, we found that it is very convenient to understand things in terms of maps. We have understood the logistic map, we have understood the behavior, we have understood how to calculate the fixed point, we have understood how to find the stability of a fixed point, and on that basis we can do a lot of things. So, the question now is, supposing you have the circular cross section Okay. Is it necessary that the cross section of the Poincare section will be circular? No, it could be any which way. For example, it could be as well like this. It is still, if you see this on a Poincare plane, it is still a quasi-periodic or a torus orbit. That is why when we define the map, it is always convenient to define the angle by which it rotates. Here also you can define the angle. For example, if from this point there is a on the next turn it comes here, then we can define this theta, and I do not care whether actually the orbit is so crooked or simply a circle.
So topologically it has to be a circle.
Yes, it is topologically a circle. So in that case it will be convenient for us to define the theta, and if we can define something like theta n plus 1 is equal to a function of theta n, we are through. We can define the dynamics.
So the cross section of the torus is a circle or any is a circle.
Cross section of the torus is a topological circle, means that if it is an ellipse, it is still topologically the same as a circle. It is a closed loop, that is all.
So how can the on the Poincare section, how can the contour that is mapped, how can it be anything other than the cross section?
Yeah, it is the cross section, but the cross section itself, see, if you are drawing such a nice thing, it is fine. But have you actually seen vada being fried in the actual fries? I mean, you take a Poincare section, you will find that it is everything other than circles. Okay, but these are topological circles. Okay.
So how do we define the center of the sphere?
Center you don't need.
So but to find the angle we need the center.
No, you don't really need the center. Though you do have the center. Wait a minute. You do have the center, but you don't need. Why do you have the center? Because how did this torus come into being? Initially it was an orbit like this, which became unstable, right? When the orbit was like this, if you place a Poincare section, it was a point that became unstable. When it becomes unstable and it develops into a torus, still this unstable periodic orbit is there, that can serve as a center. So still the unstable periodic orbit is there, so that can serve as the center. Though normally anything inside the closed loop can serve as a point from which you can, a reference point from which you can measure the theta. But it would be convenient for us if we can locate that unstable fixed point, it will be convenient for us to locate it from there. But the point I am making is that when you are defining in terms of theta, then you do not really need to consider whether it is a bent or crooked or whatever, so long as it is a topological circle, it is fine. So long as you can eat the donut as a donut, it is fine. So we have to define it something like this. Okay. Now if we can define it like so, I will define a map and see if you can see what I mean. N plus 1 is equal to the f of theta n is equal to theta n plus omega. What is this omega then? What is it doing? Suppose initially the theta naught was only this much. That means initially it starts from some datum line, it starts from this point. Then in the next iterate, what happens? It turns by an angle omega. It turns by an angle omega. So it goes by an angle omega and comes here. So this is in the next iterate, it again turns by an angle omega. and so on and so forth, right. You might say,
This is the same omega as.
yes, it is the same omega, I will come to that. Yes, it is the same omega, it will turn out to be the same omega.
Should we multiply by 2 pi omega?
No, wait, here things are normalized so that the full circle is 1. We have normalized it so that the whole circle going around the whole circle is 1. Now, that is why his question is valid. This should actually be written as mod 1, because if this omega is greater than 1, then it really makes no sense. As far as the Poincare section is concerned, it will turn only by the remainder part. So, if omega is 1.1, it will turn by 0.1. Okay. Then what is it doing? What is this fellow doing then? It is turning in each iterate by this much. What is happening on the system description? See, starting from here, it is going around it and then landing here. In that time, it has turned by an angle omega. Again, it has gone around, and by the time it again lands here, it has turned by an angle omega, and so on and so forth.
Omega small w.
No, it is omega. It is omega because it is a linear system. It is a linear system. There is no interaction between the two frequencies. That is why I am saying that. Okay. So, it is omega. I'll explain how. So, it is, what is it doing? It is simply turning by this much. Now, if I ask you, what is the winding number? Can you figure out the frequency ratio? Can you figure out the frequency ratio? By the time it comes through one of the turns, it is turned by an angle omega. So, what is the W in this case? Omega by 1. It has turned by omega around the small circle, and by the time it has gone around it in the big circle, and therefore, it is omega 1, it is omega. Okay. So, in this particular case, your winding number happens to be equal to omega. Yes, because it is a linear system. Because it is a linear system. So, normally, how would you define then the or calculate the W, the winding number, looking at the map? See, here we had defined it depending on the frequency ratios. We assume that you can, do a FFT and identify the frequencies, and then we can. But suppose we do not have that. We are only able to see what is happening on the Poincare section. Then you only have this map available to you. Then the definition of W is in each mapping, it turns by an angle omega, right? In n number of mappings, it turns by angle n omega. Generally speaking, if such a map is given, if you take f n of some theta 0 and subtract theta 0, then you find out how much it has turned in n iterations. Remember, do not take mod 1 at this stage, because you are really wanting to calculate how many times it turns. Divided by n will give you the average turning per iterate, and that is omega. Okay. In general, only in this particular system that comes out to be your omega. So, in this case, in this system only the W is equal to omega. Oh, by the way, this has to be, I have to put in here limit n tends to infinity, because we have to consider the transient dying down, and that should converge onto the actual value of the winding number. Okay. In this particular system, what is happening? In this particular system, you will say W is equal to limit n tending to infinity. Here it is n omega plus theta naught minus theta naught divided by n simply. That is why it is omega for this particular system. Okay. Well, so this is our definition of the winding number given any specific map. So is the grounding clear? Now on that basis we will take a great leap forward. So what are we doing? We are defining a topological circle. We are defining some kind of a datum level. We are defining theta from here, and we are defining theta n plus 1 is equal to from function of theta n. And we are trying to understand all those things I have been talking about in terms of such a map. Okay. The map is in theta as it turns. Now once this grounding is clear, now we can introduce a very special map that has been very well studied, because almost all the phenomena that happen on the torus can be understood in terms of this map. It is called the sine circle map. In some cases, some books you will find simply it is said to be the circle map, because it is map on a circle. It is theta n plus 1 is equal to theta n plus omega, the same as the earlier one, minus k by twice pi. This is only to normalize it, sine twice pi theta n. We have to do a mod 1. So this is the expression for the map. Now you would notice that if k is equal to 0, it is same as this is equal to the circle map that we have got. This is a linear map and this is a non-linear map, and the non-linearity is therefore quantified by this term k. So this is the non-linearity parameter. And this system actually has two parameters. Okay. This is, what is this? It is actually the frequency ratio parameter. See, we had started from the frequency ratio parameter, bare frequency ratio. So what we have here is same as the bare frequency ratio when the nonlinearity is said to be 0. So this is the frequency ratio parameter. There are two parameters in this system. Now let us try to understand how the behavior will be. First, if k is equal to 0, can you draw the graph of the map? K is equal to 0 means the old system. It is a map. So you can draw a graph theta n plus 1 versus theta n. Can you draw? Suppose this is the 45-degree line. Then here theta n times 1, so it is the something with a slope 1 till it goes till the value of 1. Then mod 1. So it again jumps here and goes. Right. So that is the character of mod 1. It comes down here and then it grows. It is actually not a discontinuity in the real sense, it is not a discontinuity in the real sense, because it is actually continuing like this, but since we are taking mod 1, because there is no point looking at how many times it turns around the small circle, that is why we have started it from here. Okay. This system can only keep on turning, and if this omega, since the omega gives the amount by which it turns, the omega is same as w, and therefore if this omega is rational, we have got a finite number of points. If the omega is irrational, we got a infinite number, drift ring we get. That means it will have a ring with all the points filled up if it is irrational. So that is the behavior of the original system without k, that means k is equal to 0. Now if you have k values, that means take a small value of k, then it results in it was going like this, it will result in a bit of non-linearity, something like this, and again it will start from here, it will have another some bit of non-linearity. So instead of this being a line, straight line as for k, it will become like this for k small, and for k large these bends will be large bends, and then it will start here. So this bend will become large bends. As a result, you see at this stage it is invertible, but here it loses invertibility, because from here for every theta n there is a unique value of theta n plus 1, but for every value of theta n plus 1 there are two values of theta n. So you can come down to in two places, and we have seen in the case of the logistic map that leads to folding. So there would be a lot of complicated dynamics that is possible in such systems, but let us work things out somewhat through logic now. Okay. Now let us write down the map again. Where did I write? Here. How to find the fixed point of this one, and when will fixed point exist? So in order to calculate the fixed point, we will say theta star is equal to theta star plus omega minus k by twice pi sine twice pi theta star. Theta star is the fixed point, cancels off. Okay. So that leads to k by twice pi sine twice pi theta star is equal to omega, or sine twice pi theta star is equal to twice pi omega by k. As you know, sine something has to be between 0 and 1. So long as k is below, k is above 2 pi omega, we are through. We will have this fixed point. So the condition for existence of the fixed point is that k greater than equal to, all right. So we have two parameters k and omega, and if this relation holds, you conclude that there will be at least one fixed point, all right. Clear? Fine. Suppose we have located a fixed point. Can you figure out what will the behavior be on the torus? Suppose we have located a fixed point. We have satisfied this condition, and depending on this condition we suppose I have located a fixed point. How will the fixed point be? Here in the graph, at some value it will go like this. So, you can easily see that here is a stable fixed point, here is an unstable fixed point. Beyond this value of 1, it will again start from here. So, it will be something like this. But nevertheless, we have identified that there is a fixed point here, stable fixed point here. Starting from any initial condition, it will ultimately converge on to that. And suppose it has converged, can you figure out what the behavior will be on the whole torus? Yes, what is your question?
So if E is greater than 2 pi omega, then there is stable point is existing.
No, I have said a fixed point is existing. It does not mean that it is stable. I did not mean that it is stable. I have only worked out the existence condition. I did not work out the stability condition. We will have to work that out separately. But supposing we have satisfied the condition and found a stable fixed point, because you can see that I was saying the more you increase the value of k, the more bend will be there. It is not difficult to see that beyond some value it will be a behavior like this. So, you are expecting a saddle node bifurcation, as a result of which one fixed point will start to exist, and when it starts to exist, it will be stable. Later that may lose stability, it is a different issue. Now, when it is stable, what is the behavior? See, here is the circle on which I am talking about the thetas. It started from, so suppose this is your theta star. That means once if it is here, in the next iterate also it is here, next iterate also it is here, and so on and so forth. So, what does it mean? It means that it does not rotate in this circle. It does not rotate in the small circle, it only rotates in the big circle and comes back here. So, what is the frequency ratio? 0 to 1. Okay. So, here the winding number is clear or 0. By the time it comes back through the big circle, it does not rotate in the small circle, and therefore, the winding number is 0.
So we can also say it to be 1.
No, wait. It is possible, but under some condition where it goes around this circle once and then lands here. That will be 1 by 1. So, under what condition will that happen? If you forget about this mod 1 and calculate this, you can easily calculate the condition under which that will happen. So, you can calculate the condition under which the omega will be 1. Clear? Can you calculate? Can you calculate the condition, parameter condition like this, for which the winding number will be 1? Since you have raised the question, let us do it. What will you say? You will say theta star plus 1 is equal to theta star plus omega minus k by twice pi sine 2 pi. Do it, you will get it. So, you solve this equation, you will get the condition. Got it? So, there will be another parameter range for which, so this solution, this theta star solution will lead to omega is equal to 1 to 1 ratio, or the omega will be 1. I am writing 1 to 1 because to let you understand what is happening. Here this is the circle and this is actually the cross section of this. By the time it goes around it, it comes back again here, so that it turns in the small circle once. Okay. You can easily find out the condition, do that. But now somebody raised the question, you raised the question that supposing this fixed point exists, but will it be stable? How will you find out the stability condition? Slope, right? So all you need to do is to calculate the slope. So calculate the slope. So stability condition. We will be able to say, this fixed point is stable when we know that there is a range, a point at which it comes into existence and a point at which it becomes unstable, right. So in order to calculate that, we will have to differentiate it. So df d theta is 1 minus k cos twice pi theta, right. Check it out. 1 goes off, twice pi comes forward, it gets cancelled. So k cos, so this is what, and it becomes unstable when this fellow is 1. So you have to put this as 1 and solve for it. Okay. So it will be stable for a parameter value between -1 that immediately gives you a range of theta. Okay. So that will give you the parameter range 0 less than k cos twice pi theta star less than 2. That is the condition under which the fixed point will be stable, right. So we have found the existence condition as this and the stability condition as this. When both are satisfied, your 0 to 1 ratio is satisfied. Again, I showed you how to calculate the range for the 1 to 1 ratio. You have to do the same thing to find out the range in which it is stable. So you can easily see that there is a parameter range. There is a parameter range in which the 0-1 ratio is stable. There is another parameter range in which 1 to 1 ratio is stable. Okay. Natural question is, how can you calculate the 2 to 1 ratios, 1 to 2 ratios? That means we are talking about mode locking now. We are essentially probing the phenomenon of mode locking. I said moon is mode locked. Moon is mode locked in what ratio? 1 to 1 ratio. Okay. Mercury is mode locked in 1 to 1 ratio. But there are many other satellites that are mode locked in other ratios. They are still mode locked. There are some 23 moons of the Saturn, and many of them are mode locked in different ratios. So obviously we are trying to understand these ratios, and in practical systems, in electrical engineering experiments, in mechanical engineering experiments, you will get enormous number of situations where you have these sequences of mode locking windows. These are very common in fact. So we are trying to understand that in terms of a toy model, and the toy model is simple enough. So let us try to understand when and what condition will there be a 1 to 2 ratio. Intuitively speaking, when a period 2 orbit exists in the system, let us try to understand what actually happens on the torus. So we have got the map. I am talking about the period 2 orbit of this map. So can you find out when the period 2 orbit will exist? Simple. Well, we know, we have already calculated the stability condition, and we know the period doubling happens when the ratio becomes -1. So, we take that condition of -1, that would be when the 2, this side is there, right. So, this is equal to 2. If you push the parameter beyond that range, push the parameter k beyond that range, then you get a period 2 orbit. That is what we have learned from earlier classes. Well, so we need to find out the ratio. We can also do this. We can obtain the theta n plus 2 in terms of theta n, same thing as we did in case of maps, and find out its existence as well as stability conditions. Both are possible, both routes are possible. Now, once we have found that, what we will get on the circle, we will get 2 points, right, say here and here. What does it mean? It means that starting from here, it went around the big circle and landed here, went around the big circle, it landed here. Okay. So, that is the behavior here. It may be also true look at look at the graph of the map. Well, when that happens, what is the ratio? No, there is no 3 here. Started from here, went around it and landed here. So, again try to visualize, sorry. So, it started from here, went around it, landed here, went around it, landed here. So, by the time it went through 2 circles here, how many times did it go around this? Once. So, it is 1:2 ratio. Okay. So, it rotates like this once, while it rotates like this twice, 1:2 ratio. Okay. Likewise, there would be some parameter range at which it will become a period 3 behavior. Say it becomes period 3 means there would be 3, 1, 2, 3 points. Starting from here, it will go around it, land here, go around it, land here. How many times did it go around the big circle? Starting from here, once, twice, thrice, 3 times. How many times did it go around it? Once. So, you have a 1/3 ratio, but not always. See, the graph of the map has this kind of a property. This part is the range at which the next iterate is between 0 and 1, and if it is in this part, theta is in this part, then it has actually gone beyond. So, it has been brought down, which means that if any iterate lands here, it has actually gone once around it. So, here the mod 1 has come into picture, but you have to understand that no, if any iterate lands here, it means that in between it has gone one additional time. Okay. Now, suppose you have got a period 3 orbit, out of which 2 points lie here and 1 point lie here. What is its corresponding behavior on the torus? Try to visualize. Try to visualize. For example, I have a situation I can show you, probably from the book. This is Hilborn's book. Can you see this picture? So, you see here there is a period 3 orbit. Out of that, 1 was in the smaller range and there are 2 in the bigger range. That means there were iterates falling in this part. Iterates falling in this part means it had gone twice. What does it mean? This what is this ratio signifies? 2 by 3. Because in between it has gone twice, there are 2 iterates here. So 2 by 3, this particular period 3 orbit means 2 by 3. Okay. So you see, we are able to understand the mode locking ratios in terms of the simple map. And in fact, all the higher periodicities are possible, and all the higher periodicities means different types of mode locking windows. Okay. Now you might ask, how big are these windows? For example, if I keep, say, your k constant and vary omega, then what do we expect? You understand my question? These mode locking windows, in that case we can paint a picture in the parameter space with omega here and k here, which means that for some, if you take a slice here, this slice would mean that for this value of k, as you change the omega, there would be some range for which 0 1 mode locking will occur, there will be some other range for which 1 1 mode locking will occur. Okay. And there will be all those intermediate ranges in which the intermediate mode lockings will occur. And it so happens that if you draw graphs, it will be something like this. This is the 0 to 1 ratio, here is the 1, 0 to 1, here is the 1 to 1 ratio, and like so is the 1 to 2 ratio. You might ask why and how. Well, these widths are relatively difficult to calculate from the map itself, because the map is a nonlinear map, but you can always do that simply numerically. Simply numerically find out for which range of omega do we have a 0 1 mode locking, which range of omega do we have a 1 to 2 mode locking, which range of, can you visualize how the bifurcation diagram will be if you keep k constant and vary omega? You already have the program written for obtaining bifurcation diagrams. You have got the system, you have got the map. Just do this exercise of keep k constant and vary omega as the bifurcation parameter and draw the bifurcation diagram. You will see a wonderful thing. Do this exercise because you already have the program written up. That is what, that was a exercise given some time back, so you already have. Right? Do it and come back with that knowledge in the next class. Then I know that you will come back with a lot of questions. Why is this happening? And then it will be my job to explain that. Okay? On to the next class.